All right, so before we begin, I would like to talk briefly about your exam. I have decided to not be an asshole and not make it on the day that we get back. So instead, we will start talking about series and parallel RLC circuits on that Monday and Wednesday that we get back, and your exam will be on that Friday then, so that you'll have time to synthesize things and also so there's going to be two more homework assignments with related to op amps. Both of them will be due after the break. If I give you your exam on Friday, that should give me enough time to get most of your homeworks graded so that you'll have some feedback and all that kind of stuff before you take your first test. So that's what we're going with.
Will the series parallel RLC circuits be on the exam?
No, that'll be the first material for exam two. In fact, exam two will be nothing but RLC circuits. So that'll be a relatively short module. I think we'll have 5 total class meetings on RLC circuits before you take your test on that.
Sweet.
Okay, so today we're going to talk about cascaded op-amp circuits, which is our last topic for our op-amp module. And essentially, a cascaded op-amp circuit is simply a circuit that contains multiple op-amps where the output of one of the amplifiers serves as the input to a second amplifier, and so on and so forth. So I'm going to draw a simple circuit here. I'm going to preface this by saying I am very much aware that this circuit could be achieved by using a single op-amp circuit. The goal here is for us to figure out how to analyze a cascaded network, and I didn't want to make something so difficult that we couldn't do it pretty easily to start with. Okay. So the circuit that we're going to be looking at is something like this. So I'm going to start by drawing my first op-amp here. And this will be a negative feedback op amp that I'm going to label as amplifier A1, which makes this pin right here the inverting input node of amplifier A1. So I'm going to say that this is V1 minus. This will be my non-inverting input pin for amplifier A1. So this will be V1 plus. And this is my output node, which I'm just going to call V out 1. Now I'm going to draw the remainder of the circuit, including my feedback path and all of that kind of good stuff. So let's say that I have a 5 kilo ohm resistor here. Maybe a 10 kilo ohm resistor here. And this leg over here is where I'm going to apply my input signal, Vn of t. And I'm going to ground this guy, like so. So I'm going to take the output of this first amplifier stage. Oh, and I'm going to throw a load resistance here just for the hell of it. So I'm going to take the output of this first amplifier stage, and I'm going to feed it into another resistor network, which will serve to bias a second amplifier stage. So this establishing the DC operating point of the system.
I don't understand what that means.
I don't know how you don't understand what establishing the DC operating point of the system means. It's the steady state condition that the system operates at because it's powered by a DC supply.
So you're just saying you're giving power without.
Yeah.
Oh, okay.
And the resistor The resistors are establishing some amount of like restrictions on voltages and currents in the system and all that kind of good stuff.
That makes.
Yeah. So this is my second stage, A2, or second amplifier A2. So this would be my voltage V2 minus. Here's my voltage V2 plus. I'm going to draw my feedback network for this guy as well. So let's put a 20 kilo ohm resistor up here. This is going to be V out 2. Let's throw another load resistor here just for the hell of it. 5 kilo ohms. And I think the last thing I need to do is apply some sort of voltage at that V2 plus pin, and I'm going to just ground that guy as well. So this looks like a fairly complicated circuit, but we can analyze it using the techniques that we've already developed in both this class and Circuits 1. So we'll start there, and then we'll approach a simpler way to analyze a circuit like this in a moment. Okay. So I'm interested in the overall output voltage of this system, or perhaps its amplifier, the overall gain of the system, which would just be the ratio of V out 2 to V in over there, okay? So I'm going to start by analyzing this circuit using nodal analysis, okay? And the reason why I'm going to use nodal analysis here, and we do have to be careful about some things, and I'll talk about it in a moment, is because all of my terminal voltages in an op-amp circuit are nodal voltages. They're measured with respect to ground. So this seems like a reasonable place to start from, okay? So I'm just going to label some nodes here. So we could call the voltage at this node VA, the voltage at this node VB, the voltage at this node VC, and the voltage at this node VD, okay? And what I'm going to try to do, and I'm going to run into a problem, and we'll talk about how we'll overcome it in a minute, is apply KCL at each one of these labeled nodes, okay? So when we apply KCL at node A, we should be able to get the relationship. So I'm saying the currents that are leaving node A are going to add together and make 0. So that would be VA minus VN as a function of time divided by the 10 kilo ohm resistor plus VA minus VB divided by the 5 kilo ohm resistor is equal to 0. So before we move on from this, are we all okay with this nodal expression? Okay. So the next thing I'm going to do, I'm going to do this over here to the right, is I'm going to try to write an equation for KCL at node B. Would you guys care to help me write this one?
VB minus VA over 5 kilo ohms.
So VB minus VA over 5 kilo ohms.
Plus VB over RL.
So plus VB over that 10 kilo ohm load resistor, all right?
Plus VB minus VC over 4 kilo ohms.
VB minus VC over 4 kilo ohms, okay? Anything else? Or am I setting this equal to 0?
So we know that no current goes into the terminals. Current flows out of an op amp.
So this is exactly the trick I was trying to catch you on, okay? So the ideal op-amp rules, and we have a negative feedback system, so we can apply the ideal op-amp rules. They state that no current can flow into or out of the input terminals of an op-amp. We are applying KCL at the output terminal of an op amp. There absolutely will be some current flowing out of that. Unfortunately, it is literally impossible for us to know what that current is without knowing what the output voltage is. Okay. So we actually can't write a KCL equation here without introducing even more variables, right? So if I called this current right here flowing out like so, I out one, then we could just add that current and set this thing equal to 0. But we won't be able to come up with another relationship for I out one anywhere. So this is actually really bad. So we can't really apply KCL at the output node of an op amp without already knowing what the voltage at the output node of the op amp is. Okay. So let's move along and apply KCL at node C. So at node C, we would have VC minus VB over 4 kiloohms. Plus VC minus VD over 20 kiloohms. Is equal to 0. And for the exact same reason that we ran into an issue when we did KCL at node B, we'll also run into that same issue if we tried to do KCL at node D. So we have two equations, but we have four unknowns. But do we really have four unknowns? What have we not done?
Ideal op amp rules.
So we've applied the ideal op amp rule number 1, saying no current can flow into or out of our input terminals when we wrote both of those KCL equations, because we inherently decided that this current and this current were 0 amps when we wrote those KCL equations. But we never applied op amp rule number 2 that tells us what the voltages at those nodes are going to be, right? So using op amp rule number 2, we could see very easily, and I'll just write these relationships right here, that V1 plus, which is the same thing as V1 minus, which happens to also be the voltage at node A, is 0 volts. And very similarly, V2 plus, which is the same thing as V2 minus, or the nodal voltage VC, is also 0 volts. So I can go back through here, and everywhere I see VA, I can just replace it with 0 volts. And everywhere I see VC, I can replace it with 0 volts as well. Okay. So we could make another quick observation here if we were so inclined, right? So we could very easily see that VB is the same thing as V out 1. So if I wanted to, I could replace this with V out 1 and this guy right here with V out 1, and VD is V out 2. So if we look at that first equation for KCL at node A, the only unknown quantity is V out 1, assuming a known input voltage, right? And whatever voltage we get from that stage is essentially serving as the input voltage to the second stage. So instead of doing all of this analysis, we could have done something much, much simpler. And I'll explain that now, okay? So what I'm going to do is I'm going to put a dashed line here. And I'm going to put it at the output node of that first amplifier. Okay. So everything to the left of this dashed line, we're going to call that amplifier stage 1. And everything to the right of this line is going to be stage 2, okay? So what I want us to do is I want us to analyze stage 1 by itself. So like mentally put your hand over stage 2 so that you can't see it. What kind of amplifier is stage 1?
Just negative feedback amplifier.
So it's an inverting amplifier like we talked about in class on Wednesday, okay? What's the voltage gain of an inverting amplifier? Should be in your notes if you took notes Wednesday.
R1.
Nope,
Negative R1.
nope,
1 plus R1 over R2.
nope.
RF, that's what it is. There you go. It's in there. It's in the back of my brain. 1 plus RF over R2. Negative RF.
Negative,
There we go.
the feedback resistor divided by R1, okay? So essentially, we could say this amplifier, so A1, or actually, let me do AVCL1 is going to be negative 5 kiloohms over 10 kiloohms, or negative 1/2. Okay. What type of amplifier is stage 2? So if we ignored the output of stage 1, or if we ignored stage 1 entirely and just analyzed stage 2 by itself, what type of amplifier is that? The same exact thing. So the voltage gain for amplifier stage 2 is going to be negative 20 kiloohms over 4 kiloohms. So from this, we could say that the overall voltage gain of the system, AVCL, is just going to be the closed loop gain of stage 1 multiplied by the closed loop gain of stage 2. So that would be negative 1/2 times negative 5 would be positive 5 over 2, meaning that whatever input signal we apply is going to get scaled by a factor of 2.5. Okay. When we did that, without doing any actual circuit analysis whatsoever, we just recognized what each of those individual amplifier stages were and how they behaved. The reason why we can do this is because we know that these configurations have really, really large input impedances and really, really small output impedances. So when we chain them together like that, all of our signal essentially survives and gets passed through to the next stage. So you will sometimes see circuits to where you may not be able to break it down into stages like this, or you may not recognize what an individual stage is. That's when you'll have to go back to this nodal analysis approach where you need to remember, I'm not allowed to do KCL at the output node, okay? So you should be able to handle it just by doing KCL at the inverting input nodes, as well as using the ideal op-amp rules, assuming they're negative feedback stages.
So just to clarify, V out 2 would equal 2.5 times VN.
Correct. Yeah, exactly right. So on you guys' exam, I will have some problems where it will be cascaded amplifier networks. And I will ask you, I'll put a box around each stage and I'll ask you, what type of stage is this? So what type of amplifier is stage 1? And then you should use that input-output relationship to calculate your output voltage of that stage and then feed that into the following calculation and all of that kind of stuff. So I'm not expecting you to do any circuit analysis whatsoever for those problems. Yes, sir.
In that aspect, like if it's a symmetry, or just like inverting on it.
So if I asked you to identify stage 1 here, I would expect you to tell me that it is an inverting amplifier. If I gave you an inverting Schmitt trigger circuit, I would expect you to tell me it's an inverting Schmitt trigger circuit, that kind of thing. Yeah. For what it's worth, you're going to have literally an equation sheet that has a picture of all of them on there with their names. So if you can read, you should get those questions right. Not to be too much of an arrogant asshole, but yeah. Okay, so now I want to look at a very commonly used cascaded op-amp circuit. So this circuit is what's called an instrumentation amplifier. So an instrumentation amplifier looks like this. It's going to be 3 op amps. So here's my first op amp. So in this particular configuration, I'm going to apply some input signal V1 of T to the non-inverting input terminal of amplifier A1. And then I'm going to apply negative feedback like so. So before I start drawing anything else, somebody tell me what type of amplifier this stage is. Does not have positive feedback. Positive feedback would mean the output is connected to the non-inverting input terminal, and that is not the case here.
Non-invert, negative feedback,
So it's got negative feedback.
non-inverting.
It is a unity gain buffer. Okay. If you look in your notes from Wednesday, it's literally the first amplifier we covered. Drew it exactly like this, except that I actually bothered to draw the supply terminals. Okay.
You want to talk about this today I was on? Do the cascaded all have to be negative feedback, or could you do a positive?
You could do a positive feedback, absolutely. So you might cascade a comparator into something else. So for example, and I think you guys will have a design problem like this, I might ask you to use a sinusoidal input signal to generate a square wave, and then use that square wave to generate a triangular wave. So you might need to feed your sinusoidal input into a comparator to generate a square wave out, and then feed that comparator into a differentiator to give you a triangular wave. So yeah, it doesn't have to be negative feedback only. You can cascade op amps into op amps, yeah. So from this node, I'm going to go into some resistor R1. So this is going to be an op amp, I'll call it A3. Going to finish up here. This will be some resistance R2. So this one is another negative feedback stage. This terminal over here is going to be our output terminal. Now I'm going to start working my way from the inverting terminal of A3, excuse me, the non-inverting of terminal A3 back towards the left with more things. So this will be resistance R4. This will be resistance R3. And now I'm going to draw my op amp A2 here. And we'll put plus here, minus here. My input signal V2 will go here. And I'll have another feedback path around this way. So this is an instrumentation amplifier.
What is it called?
Mainly because of where it's used. So this is used in a lot of control systems or instrumentation and control systems to take output signals from sensors and perform some mathematical operation on them, okay? So we can see that amplifier A1 and amplifier A2 are just unity gain buffers, right? So the signal present at this node right here by inspection, because we know how a unity gain buffer works, this is just going to be an exact copy of V1 of T. And similarly, the voltage at this node is just going to be an exact copy of V2 of T. Okay? So moving on to the third amplifier stage, that should look kind of familiar. Anybody have any thoughts on what that looks closest to?
Oscillator.
Nope. Oscillator had positive and negative feedback. This guy definitely does not have positive feedback.
It's negative feedback.
It's a negative feedback circuit, and it has an input signal applied on both the inverting and the non-inverting sides of the amplifier. We only covered one of those. Differencing amplifier, okay? So this is essentially a differencing amplifier, except that we don't have the same resistors, right? So when we covered a differencing amplifier in class on Wednesday, we had a matched pair of R1s and a matched pair of R2s. We no longer have that, okay? So for all intents and purposes, because we know how the left-hand half of this circuit works, we can pretty much just ignore it and figure out just how the right-hand half of this circuit works, okay? So I can see pretty easily, let me just annotate this right click. So I'm going to call this voltage right here V plus, and this voltage right here V minus. And so I can say that by inspection, I know Ashton loves it when I say that, V plus I'm going to find just using voltage division, right? Because I have a simple voltage divider network there. So it's going to be V2 as a function of time multiplied by the resistance R4 over R3 plus R4. And that means that that voltage V minus is the same thing. So I'm just going to put a note over here is equal to V minus. So now I could apply KCL at the non-inverting input node of amplifier A3. So that means I would have V minus, so I'm going to write that thing out again. So V2 as a function of time multiplied by R4 over R3 plus R4 minus V1 all divided by R1. So that's the current flowing to the left through here. Everybody okay with that? Now I need to find the current flowing to the right. So that's still going to be V plus. So I'll substitute back in V2 times R4 over R3 plus R4 minus V out. And this will all be over R2. And I'll set this to 0. So this looks pretty gross right now, but we can play around with this and sort it out, I think, pretty easily. So what I'm going to do is I'm going to multiply both sides by R1 times R2, okay? I'm going to do that to get rid of those denominators, okay? So if I multiply both sides of this guy by R1 times R2, 0 times R1 times R2 is still just 0. So nothing's going to change on the output side, but I'll have V2 times R2 times R4 over R3 plus R4 minus V1 times R2 plus V2 times R1 times R4 over R3 plus R4. Bless you. And I'm going to say will be equal to the out times R1. So we all okay with the algebra that I've done there. I multiplied the left-hand side and the right-hand side by the product of R1 and R2 in order to get rid of the denominators of both of those terms. So that means the term on the left should have an R2 that gets distributed through everything, and the stuff on the right has an R1 that gets distributed through everything. Okay. I can now see that my V2 terms have a common denominator of R3 plus R4. Okay. So I could rewrite this as V2 as a function of time. There's also a common factor of R4 in the numerator, so I'm going to write that as R4 times R1 plus R2. If I divide both sides by R1, that will put me with an R1 times R3 plus R4 here, minus V1 times R2 over R1 is equal to V out. And I could leave it like this, but if you look in a textbook, it's going to give you a slightly different representation of this. So I'm going to go ahead and do that part as well. Okay. So what I'm going to do, I'm going to take that R1 plus R2 term in the numerator, and I'm going to divide it by that R1 in the denominator. That's going to leave behind 1 plus R2 over R1. Okay. So I'll have V2 multiplied by R4 times 1 plus R2 over R1. And now what I'm going to do is I'm going to pull an R3 out of that R3 plus R4 term in the denominator. So if I pull that R3 out, I'll be left with 1 plus R4 over R3 down here. And this is my final input-output relationship for my instrumentation amplifier. Excuse me. So this is the last thing that I want to officially talk about for today. That being said, I have prepared some more notes to talk about a couple of other cascaded op-amp circuits that technically you guys don't have the background to cover yet, but I feel like I can explain it in enough time that we can do it, okay? Part of me is doing this because I want to give Miss Ward a panic attack because I know she hates electronics, and so it's just going to make me laugh seeing her freak out about diodes in a circuit. So I'm just being a dick. Yeah, her least favorite class, my absolute favorite class. Okay, so do you guys want to learn something else and also slightly torture Miss Ward, or do you want to knock off?
Learn.
Learn. Okay.
Still just a different thing, but it's just affected by different resistor values.
Exactly right. Yeah. And if we chose R4 over R3 having the same ratio of R2 over R1, we'd get literally just R2 over R, a differencing amplifier relationship. Yeah.
So the instrumentation amplifier doesn't have to have the unity gain amplifiers attached to it, or is that like?
No, it needs to.
It needs to.
Yes.
What do they need for?
So the sensors that you usually use in actual control systems typically aren't able of supplying their own power well. So you need the buffer amplifier to maintain that signal to feed into this guy. So for the exact same reason you'd use any unity gain buffer amplifier. Okay, so I want to talk now. This is bonus material, so you will not be tested on it or anything like that. I don't have any homework problems developed on it. It's just for funsies. In Wednesday's class, we covered amplifying signals using non-inverting amplifiers, attenuating and amplifying signals using inverting amplifiers. We added signals together with our weighted inverting summer. We took the difference, so we performed the mathematical operation of subtraction by using our differencing amplifier. We were able to integrate signals and we were able to differentiate signals, but we couldn't multiply and we couldn't divide. So I'm going to show you how multiplication and division using op amps works today. But in order to do that, we have to be real creative, okay? So let me explain some mathematical background here, and then we'll get into the circuits background, okay? So we are going to use logarithms to do multiplication and division. I know you're thinking, what the hell is he talking about? But let me explain, right? So we know that the natural log of x times y is simply the natural log of x plus the natural log of y. We all okay with that? We also know that the natural log of x divided by y is simply the natural log of x minus the natural log of y. Well, we know how to add signals together, and we know how to subtract signals. So if we can figure out how to take the natural log of a signal, we can perform multiplication and we can perform division. But then we'll have to take the anti-log or the exponential in order to actually get out the product of those signals or the division of those signals, okay? So I'm going to introduce you guys to two circuits, one of which is called a logarithmic amplifier that allows us to take the natural log of a signal, and the other one is the anti-logarithmic amplifier, which lets us do the anti-log or the exponential, right? But in order to use either of these circuits, we need to use a diode, okay? So I know that you guys were introduced to diodes in the 121, but I don't know that you were introduced to the characteristic IV relationship for a diode, right? So if I have some diode, and I'll call it D like so, this is going to be the positive polarity terminal of some voltage VD, and this is going to be the current ID, okay? And the relationship between voltage and current in a diode is this mathematical relationship. So our diode current, ID, is going to be equal to IS. So this is our saturation current. This is something that we can find on the data sheet usually. It's typically very, very small, so on the order of nanoamperes to picoamperes. Okay. So we have IS times the exponential of our diode voltage, VD, and then I'm going to throw something out here. I'm going to put a Q in front of this VD. Q is just the charge of an electron, 1.602 times 10 to the negative 19 coulombs. And down here, I'm going to put KBT. So that's Boltzmann's constant times temperature. Well, as it turns out, KBT over Q is more commonly called the thermal voltage in the system. It is a temperature-dependent thing, but at 300 degrees Kelvin or room temperature, it comes out to be about 26 millivolts. So I'm going to rewrite this as IS times the exponential of VD over VT. And I'm just going to make a note down here that VT is our thermal voltage. And it is approximately 26 millivolts at 300 Kelvin. You'll get into this way more when you take solid state electronics next fall. Sandra. Dr. Z, yep. For what it's worth, we can rearrange this expression, I believe, pretty easily and find VD as a function of our diode current as well. And we're going to use both of those relationships, right? So if I were to divide both sides of this equation, so let me do that over here, right? I would have ID over IS is equal to the exponential of VD over VT. If I take the natural log of both sides and multiply through by VT, what I find is that my diode voltage VD will be my thermal voltage times the natural log of my diode current over my saturation current. So let me just put a box around these relationships that we're going to wind up using. So this guy right here and this guy right here. All right. So let's introduce you guys to the logarithmic amplifier. Actually, that should be an I, not a Y. Okay. So in a logarithmic amplifier, it's essentially just an inverting amplifier where our feedback path is established by a diode. Okay. So something akin to this. Here's some resistor R. Here's my feedback path containing my diode.
Does the direction of that matter?
Very much so. Very good question. So a diode is a unidirectional valve for current flow, okay? Meaning that if we don't have the right polarity of voltage across our diode, then we essentially won't have any current flowing through it whatsoever. Okay?
The line up and down essentially acts like a wall.
Sure, that's one way to think about it. I always thought about it as the line is the negative terminal. That's how I remember it. But yeah. So if we look at this current relationship here, right? So we need VD to be much, I say much, but not a whole hell of a lot larger than VT. Our current is going to grow exponentially. Actually, let me draw a picture of the IV curve for a diode down here, just so that you guys have seen it. Since I'm just throwing shit at you, essentially. So on the vertical axis will be current, and on the horizontal axis will be diode voltage. So under forward bias conditions, meaning that the voltage that's applied across the diode is of positive polarity, we should see our current do something like this. So it's going to exponentially increase. Okay. If we put too large of a voltage across our diode, it will very much burn out and release its magic smoke and all of that kind of good stuff. So we do have to be careful about that. So on this side of the scale, we would typically measure currents in milliamps. Okay. If we were to reverse bias our diode, we're still going to see some amount of current flowing, but it's going to be very, very small. Okay. So we would have a curve that looks something like this, but over here, this is typically in nanoamps to picoamps of current. So very, very small amounts of current. And then technically speaking, if we put too much of a reverse bias on it, will cause breakdown, which will cause a ton of current to flow in the wrong direction and will cause the device to burn out unless it happens to be a Zener diode, which is designed to operate in the breakdown region. Okay. And again, you'll get into way more detail about the operational physics and all of that kind of stuff of this in your solid state electronics class. And then you'll get into way more applications of diodes when you get into electronics 1 and electronics 2 in your junior year as well. Yeah. So the flyback diodes were put in place to only allow current to flow in one direction through the circuit so that it couldn't travel the other way and burn your transistor out. Like I said, it's a unidirectional valve for current flow. Okay. Okay, so
So, like for flyback, is that the same thing like old teams, like flyback?
I honestly don't know. Probably the same thing. I mean, a flyback diode is a flyback diode.
Relays are inductors, and sometimes they will generate very, very large current or voltages if you turn them off really fast. So you put a flyback diode, so all the current will just go in the circle instead of busting up your circuit.
Yeah, so it essentially gets converted into heat in that small loop instead of allowing that energy to burn out other things. Yeah. All right, so this is our logarithmic amplifier circuit. And I'm going to just go ahead and denote here that this is our diode current ID, like so. Okay. So in this particular circuit, I think we can all pretty easily see that the output voltage of this circuit, V out as a function of time, is just going to be negative VD. I'm saying that because the positive polarity terminal of our diode voltage is at ground, and the negative polarity terminal of V out is inherently at ground because it's a nodal voltage. The positive polarity terminal of V out is at that V out pin. The negative polarity terminal of VD is at that V out pin. So V out is equal to negative VD here, just like V out was equal to negative VC in our integrating amplifier. Okay. So since V out is equal to negative VD, and I know that VD is related to my diode current through this relationship that I have boxed up in blue here, I could write this as negative VT times the natural log of ID over IS. Well, I think it should be pretty easy for us to see that our diode current is just going to be Vn divided by R by applying ideal op amp rule number 1 in KCL at that non-inverting input node, right? because we know that the voltage present at the non-inverting, or excuse me, at the inverting input node will be exactly 0 volts because we've got the non-inverting node grounded. The current through that resistor will just be Vn over R, and that current has to be the same as the diode current that's flowing through KCl. So I can substitute that in, and I get negative Vt times the natural log of Vn divided by Is times R. So my output signal is related to the natural log of my input signal. So that's why this is a logarithmic amplifier. Okay. To make an anti-logarithmic amplifier, we're just going to swap the position of the diode and the resistor. So we'd have something like this. Let me see. Minus plus. I'm going to put a resistor in my feedback path here. I'm going to say that this is my diode voltage VD. And this is my diode current ID. And I believe we can all see very easily that our diode voltage is just our input voltage for this particular circuit. Okay. So I'm going to write a relationship here. ID will be equal to, and I'm just going to scroll up here. I'm going to use this guy, IS EXP times VD over VT. And by inspection, I can also say that my diode current is just this current flowing through the resistor, which is negative V out divided by R. And rearranging those two relationships, I'll find that my output voltage for this particular amplifier, V out as a function of time, is just negative Is times R times the exponential of my diode voltage, which is just Vn in this case, over my thermal voltage. So these are our logarithmic and anti-logarithmic amplifiers. And just to make sure we understand what's going to happen when we substitute when we take the output of a logarithmic amplifier and apply it as the input of an anti-logarithmic amplifier. So this is more of a mathematical exercise. We would have V out is negative Is times R times the exponential of, so in this case, Vn is going to be the output signal of this logarithmic stage. So I'm going to put negative Vt times the natural log of Vn over Is times R. All of that will be over Vt. So I see that my VTs cancel out. So what's the exponential of the natural log of Vn over Is times R? Negative Vn over Is times R, right? So I would have, sorry, negative Is times R times negative Vn over ISR, and negative ISR cancels negative ISR, so my output is literally just my input signal. So I've undone that logarithm by using the anti-log amplifier, okay? So the math bears out. So if I can now, so now let's sort out how we do the other things, okay? So coming back up here, I need to take the natural log of one input signal and the natural log of another input signal, and then add those guys together. So how might we do that?
Cascaded amplifier.
So I'm going to have to do a cascaded amplifier, but how am I going to do the addition specifically? So some sort of summing amplifier. Absolutely right. So let me come down here. Let's write multiplying signals. So I'm going to take two logarithmic amplifiers. So let's call this V1 into some resistor R I think I have to draw this smaller because it's going to wind up being 4 total op amps. Sorry about that. So there's my first logarithmic amplifier. I'll do another one down below it. So the output of both of those logarithmic amplifiers are going to go into an inverting summer, okay? So the inverting summer had some resistor here.
And the resistances will be the same.
So we'll talk about that in just a second. So let me just, I'm going to put a dashed blue line here. And then I'm going to put a dashed red line over here. So this is where the, between these two lines is where the addition is taking place. So this is our inverting summer. Over here to the left was our logarithmic amplifiers, obviously. Okay. So we can establish a gain in this inverting summing stage by choosing those resistor values, okay? So if we want both of those signals to be not scaled, okay, then let's call this RS, RS, and RS. I'm just using the S's for summing, and this will scale each of those signals by a factor of 1, essentially, okay? So that we're just adding together the output of those signals without any additional amplification. If we wanted to amplify those signals further, we would just need to change the value of this guy right here, make it larger, and it makes both of those signals larger. Make it smaller, and it makes both of those signals smaller. Just like you would see with just the regular inverting summing amplifier, because it's just, its job is just to add signals together. Okay.
If you were using like signals from some source like a piezo or something, could you use the summer as your amplifier, or would you need the unity gain buffers at the beginning?
You need a unity gain buffer at the beginning. So the next thing we need to do, so let me mathematically write down what's going here, right? So we know that at this point right here, our output voltage, I'm going to put, is proportional to the natural log of V1 of t. And here, our output voltage is proportional to the natural log of V2 of t, just based on this equation up here, right? Where Vn would be V1 of t on one of them and V2 of t on the other, okay? The summing amplifier, so at this point, we have the natural log of V1 plus the natural log of V2, which is the same thing as the natural log of V1 times V2. And so now we need to do the anti-natural log so that our output signal looks just like the product. Okay. So this is where the anti-logarithmic amplifier is going to come in. I'm just going to throw a resistor R there. Okay. And this R and the R's on the left-hand side of the circuits are the same, so that we're only going to get back an output that is V1 times V2. So I want to think about what we did here, okay? So this is a cascaded amplifier system where each stage is performing some critical role in the desired mathematical operation that we're trying to do, okay? So when I give you a design problem dealing with cascaded amplifier circuits, like I might tell you, you want to add some signals together, introduce a DC offset, think about what each amplifier is capable of doing, and then what order those mathematical operations need to be carried out in order to produce the desired output voltage. And that's the order that you put them in when you cascade them together. That's analog signal processing design. Literally just, well, I need to do some sort of addition, so I'm going to have a summing amplifier. And I need to add some sort of DC bias, so I could do that with a summing amplifier. I could also do that with a differencing amplifier by adding a negative signal in. I might need to integrate something, so I'll obviously need an integrating amplifier or something like that. So if you ever need like a phase shift, so you want to convert a sine function into a cosine function or vice versa, that's going to be an integrating amplifier or a differentiating amplifier, because you know the relationship between sine and cosine is a 90-degree phase shift, which happens by integration or differentiation of those signals, right? So just think about what it is that you're trying to do and what the order of operations needs to be, and then chain the amplifiers together in that order. Okay.
If you're trying to turn a sine signal into a cosine signal
Mhm.
and you use integration, usually whenever you integrate sine to, it becomes negative cosine, right?
Mhm.
So how does that negative play in? Does it matter?
So it doesn't really matter, and our integrating amplifier automatically has a negative sign thrown out front. So if you used an integrating amplifier like the one that we developed in class, it will automatically get rid of that negative sign. Whereas if you used a differentiating amplifier, you might have to pass it through just a non-inverting amplifier with a gain of 1 to flip that negative sign into positive or something like that. So like I tend to use differentiating amplifiers more so than integrating amplifiers because we kind of fudged things a little bit with the explanation for the integrating amplifier by doing our integral from negative infinity to t so that we wouldn't have to worry about initial conditions. But in a real system, you will have some initial conditions. You fix that by placing a resistor in parallel with your energy storage element, which forces the initial condition to be 0, but that also slightly changes the relationship of the circuit. So really you need to choose that resistor so that at the frequency of interest, it looks effectively like an open circuit. But that's, when we learn Laplace transform to analyze circuits, the math behind that will be way easier than it would be to do right now. So that's why I didn't do it here. Yeah. So if we wanted to do division, scrolling back up here, and I think we're almost out of time, so we'll just talk about this. So division of signals means that we need to just subtract our logarithms, right? So the logarithm of our signal 1 minus the logarithm of signal 2. So the only change that we would make is instead of having an inverting summer in that middle stage, we just put a differencing amplifier there. And that's how we divide.
That's cool.
Yeah. It's just a bunch of building blocks. They're literally we're building systems using op amps like they're in Legos. We need it to do this, so we're gonna put this one, stack it with this one, stack it with that one.
Will we ever learn about like what's inside the triangle? Because I know that there's a layer of abstraction in there.
So for sure. So in your electronics class, particularly electronics 2, so 336 that you'll take in the spring quarter of your junior year, you'll learn about a lot of the building blocks that go into op amp circuits. And then if you choose to take integrated circuits, you'll actually design your own op amp. Okay. So it's a bunch of different transistor circuits. So a single stage op amp, I'm getting into the weeds here. But a single stage op amp circuit internally is actually relatively simple. Okay. So you would have a couple of transistors like this. And I know that you guys don't know how to analyze this circuit, and I can't do it off the top of my head without my notes, so I'm not even going to try, just to be clear here. So this thing right here is called a current mirror, and it's being used to load what's called a differential pair amplifier. So here's VN1. VN2. And then down here at the bottom, you would usually bias this with a current source in an ideal case. And for what it's worth, a current source is just another transistor.
That's all.
Where you're using this guy at some fixed DC bias voltage to force a particular amount of current to flow through this guy. This circuit essentially just steers current around. And then we would take our output voltage to be here. Now, the reason why the internal circuitry of a practical op amp like we might buy from Mauser or DigiKey or whatever is way more complicated than this is because This particular configuration has a really high input resistance, but it also has a really high output resistance, which is not what we want for a good op amp. So we can only drive capacitive loads with a circuit like this, which isn't useful in a lot of applications, okay? Also, the gain of this particular circuit isn't going to be crazy huge. So instead of hundreds of thousands, it's probably on the order of a few hundreds tops if we design it well. We can make it better by doing what's called cascoding, which is stacking transistors on top of transistors, essentially. But that's going to make our input resistance even larger and our output resistance even larger. So what we would do is we would take the output of this system and feed it into another gain stage so that we can get larger gain. And then we would feed it into a push-pull output stage, which will cause our output to be able to swing between our positive and negative supply rails. And guess what? It also happens to have a really low output resistance. So a op amp in and of itself is actually a 3-stage transistor amplifier in its most basic form. And then you could analyze those stages and be like, well, actually, that's another couple of amplifier stages buried in there. So you can, it's inception or whatever. It's each amplifier stage is actually multiple amplifier stages if you really look at it.
It's a rabbit hole.
Yeah, exactly right. But anyway, this is well beyond the scope of this class. So you guys have a great break. Stay safe, all of that kind of good stuff. I'll see you when we get back and we'll talk about RLC circuits.